Hello. In this session, we're going to look at concrete masonry lintels, and we'll include a strength design example. My name is Sam Rubenzer. I am the founder of Force Consulting and the managing director. I'm a licensed structural engineer in the state of Illinois and a professional engineer in several Midwestern states. I have my engineering degree from the University of Minnesota and an MBA from Marquette University. So in this session, covering masonry lintels, we're going to be looking at what's in the TMS code. TMS 402 essentially defines it as a member designed primarily to resist flexure and shear induced by loads perpendicular to its longitudinal axis. So what does that mean? So basically our learning objectives are going to be looking at lintels, kind of covering some of the basics, looking at what different options we have for lintels, masonry walls, what different types of materials we have for options, what some different choices that we make relative to the masonry elements, which affect the lintel load quite a bit. And then we'll look at high-performing lintels and some finite element analysis tools. And then, like I said, a strength design example. Some of the different steps for masonry lintel design. I would first look at defining materials, kind of the strength of masonry, geometry of the walls and the opening size. All of that stuff is going to affect the overall lintel. The loads on the lintel, kind of what some of the different elements and geometry of some of the elements that we define, what those look like, and some of the different design options. Material choice, believe it or not, does actually affect the overall analysis and forces on the lintel as well. So let's get into this. If we look at the actual definition of the materials, kind of the strength of masonry, really kind of similar to the other masonry elements, we have the same similar concrete elements where we have the concrete masonry units. We have the mortar and the grout, all concrete elements. And then we have reinforcement. This time we have some horizontal reinforcement, could actually have some tie and stirrup reinforcement. If we look at a little bit in kind of an example condition here, different types of blocks that are going to be used for masonry lintels, especially with multi-course lintels. You can see that the lintel block shapes, the U or W shapes, really have that closed bottom. So when you look at a lintel from the underside, you're going to see a nice uniform concrete surface. You're not going to see the different cells and openings. So you're going to see with lintel block a nice smooth surface at the bottom. But other shapes can also be included within the lintel. Certainly if you have multi-course lintels, you could have standard stretcher blocks that could be used. You could have bond beam blocks, these flow-through bond beam blocks that have webs that actually can be broken out so that you can place reinforcement. Could be a little bit easier to grout, so on and so forth. So a lot of different types of elements that we can use for the lintels. And then again, we also have a look at what the actual strength of materials are. Again, we've covered this in other sessions, but looking at what the different choices are with concrete masonry units. We have from 2,000 all the way up to 4,500 for different concrete masonry units that would be covered within the TMS 602 code. You put it with a type S mortar, and we get an overall strength of masonry type. Could be 2,000, 2,500, or 3,000 for the design. I do also look at lintels maybe a little bit more in the importance of the overall strength of masonry. So looking at whether or not the strength can be designed at higher strength like 2,500, or maybe we have to stick to the F'(M) of 2,000. F'(M) could be as high as 4,000 though. Lintel designs do change quite a bit with the overall design strength, the depth that you have to design with. So really making sure that we have a good understanding for what materials we have, what the overall strength implications are, is going to be really important for designing our masonry lintels. The geometry of the wall, the opening size, that's going to make a big difference for the overall design. Looking at movement joints at openings are going to be really important to understand where those joints are. Really want to make sure with the reinforced masonry walls, we're looking for control joints to be away from the openings. That's going to be really crucial for the overall lintel analysis for the forces that you're going to get into the lintel. When the control joint is going to be next to the opening, it's going to be more like a simply supported element, and it's also going to have a lot more loads that it's going to have to be designed for. So looking at control joints and where they go is going to be extremely important. As we've addressed in other sessions, looking at the different options that you have for movement joints, control joints, and what types of horizontal reinforcement that you use. All are going to be covered within these different guides. The CMHA Tech 9-25 does a really good job of summarizing all the different documents that used to be available from NCMA. So really looking at the different options again for moving joints. Again, we have another session that covers this pretty thoroughly. But looking at the different horizontal reinforcement, we could go with a lower level of horizontal reinforcement and regularly spaced control joints, what I like to call option 1, or option 2, going with horizontal, increased horizontal reinforcement, rebar reinforcement, and bond beams in a sense, and then minimal control joints. And then option 3, similar to 2, being a combination of joint reinforcement plus bond beam reinforcement, and then again, increased spacing between control joints or no control joints in that option. Within those guides, again, we do look at diagrams like this where we can see that it's still recommended within the guide when we have an unreinforced wall, but obviously most of our walls that we're looking at today are going to be reinforced elements. And so making sure that once we have reinforced masonry elements, we look at control joints away from the openings, which would be very prudent. Similar diagram, but this time showing the reinforcement, showing that we have plenty of reinforcement to prevent any cracks from occurring at the corners. And so that's going to be a really nice design option. Again, covering some of the different horizontal reinforcement requirements to eliminate control joints or eliminate the need to put them regularly in the wall. So again, we have here just listed bond beam reinforcement. So bond beams maxed out at 48 inches on center, or the combination of bond beam reinforcement and joint reinforcement. Because the joint reinforcement is distributed everywhere, we have the ability to increase the spacing, so to speak, with the bond beam reinforcement and still meet some of the reinforcement ratio requirements for the design. So again, really quick kind of illustration of what that looks like. So option number 1 being the regular control joints, regular movement joints in the masonry wall with low levels of horizontal reinforcement. And then option 1 with openings. Obviously, the openings do end up requiring a few more movement joints. And so you can see the walls getting kind of broken up a little bit. Option 2 is going to give us a lot more lateral capacity just because we have a lot longer wall. So the in-plane shear wall capacity would certainly go up. The design certainly goes up in terms of the overall capacity and strength. And then option 3, looking at, again, joint reinforcement and then less bond beams. So again, why we're talking about this in the lintel sessions, because we have openings with lintels over them. We already have the opportunity of taking the horizontal reinforcement from those lintels, making that continuous, maybe taking the sill reinforcement, making that continuous, and then using the standard joint reinforcement, really not adding a lot of reinforcement to this overall design to be able to have more freedom or more liberty about where we want to put the movement joints in that perspective. So again, looking at a design like this, where we have minimal places to put control joints anyway, and we have very large, nice places to put continuous masonry lintels over the top. And so you can see here, a nice continuous lintel over the top of all of this design would work very well. And here you can see one of the elements as constructed. So again, making sure that we have a good understanding then for when we have a continuous lintel, what type of analysis is going to be required for that element, is where we start to look at finite element analysis as a very good tool for understanding the overall forces in those masonry lintels. And so certainly that's going to be the type of element that we need to be a perforated shear wall. So certainly looking at the forces in a lintel relative to the forces in the shear wall, kind of how the flow of forces kind of moves through that element. All going to be very important. So where we put that control joint, though, really has a huge impact on all the other elements of this design. So loads on lintel, again, how do they get distributed through the wall to the lintel? Like we just talked about, the control joint has a big part in that. Making sure that we get the loads right. We have distributed loads, we have uniform loads, point loads. We have some arching action that we can consider once we have the movement joint, control joint in the right spot. So making sure that we both understand not just the lateral loads here. You can see the lateral forces that we maybe want to look at for the lintel elements. We do have a lot of exterior walls with masonry lintels, so certainly making sure that we have the horizontal bending capacity that we can consider. And then all the other elements that are sized and framed around it and what the different forces are certainly going to affect what loads need to be transferred then to that lintel as well. Certainly with the vertical forces, here I can show what maybe some of the forces would be at the roof elements. If I just sketched in maybe how I would think the masonry wall would be able to support those forces. There you can see the blue lines, blue arrows, kind of defining really what we're going to talk about next is arching action. When we have a masonry wall, the concrete elements, the masonry elements, do have the tendency to want to support those forces based on stiffness, and really that's going to be, as long as we have continuity or continuous elements from the area above the opening to each side, we have the ability to consider something like arching action. So there is a document from NCMA that has a nice little diagram in here for looking at the forces on a masonry lintel when we have the ability to consider arching action. So that's going to be a pretty important aspect of it, but let's just start with some of the basics of what an arch looks like, what some of the different forces would be with an arch. So if I just took a very simple arch and we looked at kind of this 3-hinge arch, if we just put a load at the center, we know that that force is not just going to be a vertical force at the supports. We know that when we look at a kind of a free body diagram of half of the arch, we know that we have a vertical component and a horizontal component that we have to resolve. So there's going to be some thrust loads. Again, if we have a 1-to-1 kind of arch, so if a 45-degree angle would be kind of a 1-to-1 slope rise to run ratio, then we know that we would have as much thrust as we have vertical load. So again, understanding what some of the forces are is going to be really important for understanding what the thrust load that we have to support. If we have a different aspect ratio, if we have a very tall arch, we would have very little thrust loads that we have to analyze and design for. So again, this guide gives us a really good, simple approach to look at arching action, what some of the different parts of the wall. Again, we just looked at control joints, where control joints go relative to the opening, have a huge part in defining what the overall force is on the lintel element. But then again, making sure that the jambs or the areas on each side of the opening can actually resist those thrust forces, and we can consider that arching action. So again, just a really quick illustration of what that would look like. Again, if we did put control joints at each side, then we would have no ability to have that arching action. There'd be no ability to transfer that thrust force at each side. So again, lintels in this design would have to be designed for all of the load above the opening. So all of the roof load, all of the load in the wall, the self-weight of the lintel itself, quite a bit of force. But when we can consider arching action, again, really then the lintel only has to pick up a small area local to the lintel, because the wall would be able to arch to each side through some vertical forces and some thrust forces to each side, on each side of the opening. And again, we've seen this in even old Roman architecture. We know that this works, especially when we have multiple openings that are stacked. We know that the thrust loads, in fact, don't become much of an issue because they actually cancel out. We have the end, if you had a series of openings, the end opening would have the thrust force that we'd have to consider, and we'd have to have a little bit more of an abutment there. But again, just recognizing what the actual thrust loads, what the implications of that are. But once we have that, we know that we have a lintel that can be designed for a lot less force. So within that same reference document, we have arching action that we can consider. And if we can consider arching action, then we know that the only forces that we really have to consider, and again, this is an empirical method, a little bit of a conservative approach to what the overall understanding would be. But even through this approach, we know that if we have arching action, the only loads that we have to consider are the self-weight of the lintel itself, the wall weight, so kind of that triangular area underneath the arch, and then any concentrated forces. Again, that's a kind of a conservative step to put there, but making sure that any concentrated loads on the wall above will be considered. But if we didn't have arching action, we know that we have to have the self-weight plus the wall weight, the entire wall, not just a triangular area, the entire wall, any concentrated forces, but any floor, roof, uniform loads or concentrated loads, all of that stuff would have to be resolved by the arch. So, by the lintel. So that would really be a lot more load, a lot higher demand on the overall design. looking at and maybe considering what software would be able to help us with some of the finite element analysis software would be able to help us with. Maybe we can understand a little bit more about this. Again, the traditional way to look at a lintel would be the simple analysis, pinned end kind of approach. We know that lintels are integral with a wall on each side of it, so we know that we also could consider that a fixed end element, and then we know we have finite element analysis that can help us have a better understanding for the overall design of these elements. So sometimes these openings can be relatively large. Again, finite element analysis can certainly help us have a very good understanding for what the forces would look like in large openings. But then certainly in some of the other buildings with smaller openings, we can look at this and we can animate the shape and we can see what some of the different deflected shapes look like. But we also can look at a local level and see what the actual lintel forces and the bending of the lintel and how that affects the jam and how those elements are really going to be operating more like a moment frame than they would be these isolated elements in design. So finite element analysis does give us a nice ability to look at the forces in the lintel and look at and see what some of the different forces in the adjacent elements would be for the design as well. So it's not a separate entity. The masonry lintel is really going to be part of the overall wall mesh, and certainly looking at the forces, I think it help us have a better understanding for lintel design. So here I'm going to look at a couple different openings just so we can see what some of the different options are and kind of how it affects some of the different forces. So we can look at one example with a 6-foot opening and another example with a 14-foot opening. For the 6-foot opening, we're going to have a 28-foot high wall. So 20 feet above the opening is where we're going to enter in some loads. We can see what some of the different axial forces are in that wall element. And I think looking at the different color contours that you have here, the red colored areas are going to be the low axial forces. And then you can see the axial force stress is going to increase in the green to the turquoise, to the blue, to the dark blue, to the purple. Well, what you see above the opening is you actually can see the forces start to get higher and then they actually get lower because obviously at the opening we don't have any support. So you can kind of see the natural arch being created in the overall wall elements as it supports the load from the roof above. So we can actually look in within a finite element analysis, we can actually see what the actual forces are for those elements. We can see again the axial force in the area above the opening goes from small at the roof to larger and larger, and then diminishing again as it gets near the opening. We can also look at the thrust forces from the masonry. So again, we can look at both the vertical and horizontal effects of having the opening here and how the forces are going to flow and transfer around. Again, we can see, that we also have opposite and opposing forces. So that's why you can see the different stress contours on each side. We can actually look at the numerical amounts of what the actual forces are. So if you remember what some of the different forces were from the previous slides, we're looking at like a 20-to-1, not a 1-to-1 ratio, but a 20-to-1 ratio for the actual vertical loads to thrust loads. And that's just because we have a very deep arch. We have a large area of opening or a large area of wall above the opening. So it really allows that aspect ratio to be relatively low. We can then also look at the forces for the lintel area. We can see what the shear forces are going to be for the area just above the opening. Here you can see I included the entire strip to each side of the opening as well. You can kind of see that force kind of flowing through those elements, but you can see that shear is spiking at the edges of the opening. We can also see the moment. If we look very close or look at some of the different values that you can see there, you can see that you have a positive moment at the center of the span. We have some negative moments at the ends of the span, kind of indicating more of a fixed condition for the lintel area. So very same set of results. We're going to look at the example number 2. We're going to look at a 14-foot opening. Again, same wall height, same area where the roof loads are going to be coming in. Again, we can see some very similar color contours. We can see some arching action occurring. We can see what some of the axial forces are going to be on these wall elements. We can take a closer look at the actual forces themselves. See how, again, And here you can see the forces are quite a bit bigger in the area above the opening, almost double. Well, it's more than double the actual size. So that made sense if I sum up the forces across the strip when I have twice as wide of a strip. But you can also see it diminishes all the way down to 0, which is what we would expect. Also, very interestingly, we can look at the thrust loads. We can see with the values for the thrust loads, we can see how the thrust loads actually occur. The highest thrust loads are actually at some area high above the opening when we get down to the opening area, but none of them are all that high. So we're about a 10-to-1 ratio. Even though we have a very large opening, we can see we have a 10-to-1 ratio for the axial force to the thrust force that we're going to be needing to design for in this in these wall elements, in the jam elements next to the openings. Lastly, we can also look at the shear forces that we have in the area in the lintel elements above. So again, you can see those highest at the ends of the lintel. One thing to note is when we do look at finite element analysis, this is going to be looking at the forces across these strips. Again, if I have the limited depth of the lintel, it's going to be smaller forces. If I increase the size of the lintel elements, so that's increasing the actual size of the elements that I'm summing the forces across, you can actually see the forces go up. And that makes sense. Again, we're grabbing a larger area, larger cross section to actually look at the forces. So you can again see the shear here. And again, if we looked at those larger forces, you can see the higher moment as well. Again, the moments, again, you can see positive in the center. You can see negative at each end, again, indicating some fixity for the lintel elements to the jam areas on each side. One of the things that I think is really important, so we looked at this with a finite element analysis, but I think it's also really important to look at what the actual hand calcs would be. What are the forces? What would they show you for the overall design? So again, looking at kind of the two examples, again, example 1 with a 6-foot span, example 2 with a 14-foot span, all the same geometries for the wall and the loads. You can see the actual shear values that I get. And then what I list at the bottom is different analysis options. So if I would consider pinned end, so a pinned end of a lintel element, no arching action, you can see what the shear forces would be for the 6-foot opening. You can see what the shear force is 14.2 for the larger lintel length. If I have fixed end and no arching action, you can see what the shear forces are going to be identical, and that makes sense. And then I look at 2 more analysis options, pinned ends with arching action. So as the with arching action, the key there is obviously we're just going to have that triangular area, again, that we're designing for. We're looking at the shear for just in that triangular area. So you can see the 1.8 and 4.2 to be our shear values. And then I know that my finite element analysis, I know what that actually gave me for shear values. Again, it gave me 2.3 for the 6-foot opening and 3.9 for the 14-foot opening. So again, you can see they track pretty close to the with arching action, which makes sense. We could see the actual arches forming within the plate elements based on looking at the contour maps. So again, you can see that kind of confirms arching action would be considered. Even here, just with looking at the shear force, arching action pretty similar to the finite element analysis that we're doing. The other thing that we could look at, not just shear, but let's just look at moment. Again, looking at the 2 examples, 1 and 2, 6-foot to 14-foot, you can see what the different implications of the moment force in these designs. So the different analysis options, you can see that pinned end in no arching action having relatively high moments, 9.1 to 50 for the example number 2, 49.7. But then you can see when I look at fixed ends and no arching action, of course, my maximum moment drops down a little bit because I have negative moment and positive moment in that span. Now, if I look at pinned ends with arching action, fixed ends with arching action, you can see that the moments continue to drop considering all the different options. And then again, we can look at and see what the actual the moment, how it correlates to the finite element analysis. So again, you can see fixed end with arching action, again, corresponding pretty well with the finite element analysis. but we also can see the fixity, fixed end now being something that we can somewhat validate through our finite element analysis. So we can see it now. Arching action, fixed ends, that correlates pretty well with what we're doing with finite element analysis. So you can see that that would be the most comparable solution. So you're going to see, again, with finite element analysis, we're going to have far lower forces that we would be considering than if we were looking at the openings with pinned ends and no arching action. The other thing that I think is very interesting is when we look at the actual forces that we have here, the moments that we have for the actual different elements. So using a different type of material and having to put control joints on each side would really drive the analysis to be pinned end and no arching action. So that would, in fact, increase the actual force that you would have to design for versus what you would have for an element that would be more integral with the wall. So a precast lintel or masonry lintel that could be more integral with the wall on each side. So that's why you can see that actually designing, you can design for a lot less shear for the actual material that's similar to the wall, and you actually can design for a lot less moment. So looking at the two different types of or the different types of options that you have for lintels do really make a difference. If the lintel material does require you to add in movement joints, it really does reduce the actual ability for the wall and on both sides of the opening to actually support and work with the lintel element, which is why you can see the forces and the demands going up quite a bit in that analysis. So again, steel lintels have control joints at each end. They really should for a variety of reasons. And masonry lintels or precast lintels don't have to have control joints. They shouldn't have control joints at each end, which really does change the overall analysis quite a bit. And there again, you can see some of the force comparisons. So then we get to the different design options. Again, we can look at the different types of lintel material, how it affects the overall design. Again, we would consider masonry to be the best option, again, because it's going to be similar from the aesthetic perspective, but also from the analysis design perspective. Steel, which would be the more common today element that is being used, but I think that's more of a historical reason. I don't think there's a good reason to put in steel lintels in a masonry wall today. It really does create a lot of complexity, and it's probably not worth the trouble. And then we have the third option there, precast, which is going to be pretty similar to the masonry elements, but also going to be something that could be integral. So again, we have different types of precast lintels, which I think are really nice and would correlate well to the rest of the overall masonry design. So here you can see these lintels that really look like stretched out U-blocks. They work pretty well, but certainly they would need to be ordered. They need to make sure that they're modular. We got to make sure that it's coordinated from the overall construction. They are resistant to fire, which is very good, but it certainly could be a little bit of a scheduling issue if the elements aren't ordered early enough. There's sometimes some shipping. There's not as readily available as different masonry elements. So here you can see a project where we actually use some of these precast lintels in the project. It went very well. The next option material-wise for lintels in a masonry wall would be steel. Very common should they be. They're scheduling critical. They're long lead time for a lot of these elements because there's other parts and pieces that have to be connected to them. You need corrosion protection. You need flashing and treatment to these elements to make sure that they don't rust. You need bearing plates very often, and those also need some corrosion protection or need to be considered from the overall aesthetic. It's not resistant to fire, so it's going to be a lot less fire rating. There's a thermal bridging issue. Oftentimes for these elements, it's going to take whatever is on the outside of the wall, bring it to the inside of the wall. That's certainly a thermal bridging issue that the overall transfer of hot or cold to the inside, but it's also a thermal bridging, or it's also a loading issue as the steel elements are going to change size because they're going to be changing temperature much more rapidly than the masonry elements around it. So really that's going to be shortening and extending those steel elements relative to the masonry wall all around it. What happens in that situation is you end up with some stress concentrations due to these steel elements transferring some of that cold or hot temperatures. So again, thermal bridging is more than just the transfer of heat or transfer of cold. It's also the actual changing of the shape of the size of the element and the forces that it's imparting on the masonry elements around it. So again, really, it was just added to masonry walls to solve shoring, but it seems to be maybe a lot more complicated. So steel lintels are being used because of the shoring, but really they're not faster, not easier. So really they're not needed for the most of all for the design. There's some really complicated elements that should be added to the overall steel designs, like these U-bars and stuff like that. If you're going to have a masonry wall with a steel lintel, adding some of these details are going to be really imperative to make sure that the overall design goes well. So what ends up happening is you tend to have a lot more material. It's going to be a lot more expensive. It's going to be efficient. It's not going to be environmentally friendly. There's not going to be a lower carbon footprint. With the steel lintels, you can have a much higher carbon footprint in the design. So masonry lintels, we like to talk about those for a lot of good reasons. It really doesn't require any more demands on shoring. You have to educate the contractors in terms of what's available in terms of prefabrication, or looking at different types of shoring systems that are much more readily available. We don't need to leave the shoring in the wall, is what I like to say for the steel lintel options. We can just put in some shoring, very simple elements, and then remove it and build with masonry for these masonry lintels. So masonry lintels are going to be very integral, going to be very robust, they're going to have a lot more capacity. We can see that there's many benefits for these masonry lintels, which we showed through a variety of these different presentations, but certainly with the movement joints and having continuous masonry lintels, having a much more high performing elevation here in this perspective. So looking at the overall multi-course masonry lintel, again, remembering that we have different types of blocks that are going to be used to be able to enable us to have these elements and the continuity that we would need for that design. So with that, let's go ahead and take a little bit of a step to the side here about looking at an example for a masonry design and what some of the different implications are of some of the different design checks that would need to be made. So we'll look at a strength design for an 8-inch concrete masonry beam lintel section for a moment of 320 kip inches, which would translate to an ultimate moment of 448 kip inches. And here for this design, we're going to use an F'(M) of 2750. So for the design, we certainly can enter in all the different components for the design. We can look at arching action, developing somewhat of a checklist to make sure that arching action can be considered. We can see once we have arching action how low the forces would need to be for our overall design. So a lot less than maybe if we didn't have arching action. We can see that we would have, again, a much higher moment that we would have to use. So again, the ultimate moment of 448 kip inches would translate to an ultimate moment of 37.33 kip feet. So not having arching action would really demand us to design the lintel for all of that moment and all of that force for the overall design. Certainly for that moment check, we are going to look at the all the different equations for capacity for the design. We can see that we have an area of steel that would be required of 0.3 inches squared. So if we had 2 number 4 bars for this design, we would have enough reinforcement for bending capacity. We could also then look at the shear check. We can look at the actual shear in the actual moment or in the lintel and see, what the number of courses that we have. If we have 4 courses, we have plenty of capacity for shear to resolve those forces design-wise. So we can look at it with a very simple tool, a spreadsheet. We can also look at it with the Masonry software program, looking at the very same example where we're looking at the 4-course lintel beam, 8 inches wide. We have 2 number 4 bars that we consider for the bottom reinforcement. We can see what some of the different design checks would be for that element. Here within the program, you can see what some of the different moments. Again, the moment of 37.33 kip feet, and then you can see a shear of 22.4. So you can see the moment and shear diagrams. We can then also do a section analysis where we can actually see the forces calculated for the section, for the reinforcement, and for the compression block that we have for the masonry elements. We can look at our strength design. We can see what our VMN, we can see what our overall moment capacity would be, 0.9 times 54.05, giving us an overall moment capacity of 48.65. So that's going to give us a utilization ratio of 0.767 for our design. And then the last thing that we want to do is we certainly want to do a deflection check. We can look at all the different parameters for deflection to make sure that we have enough moment of inertia to have a element that's going to be rigid enough to not exceed any of the deflection requirements for our masonry designs. So again, a lot of different options. We need to look at the analysis options to actually see what the forces are before we actually get into the strength and serviceability checks. But you can see we have some nice tools to be able to do that for strength design for masonry lintels. So earlier I did mention some unique shoring options. So here's one of the different shoring options that is now available, where we actually have elements that span between jambs so that they would have basically a steel element that can be removed to shore up the masonry element so that they can be built in place. Then once they're built in place, then we can certainly have all of the reinforcement and all the continuity that we're looking for with our designs. Again, remembering that having finite element analysis is going to be pretty important if we want to consider all the different stresses and forces that you would have for these elements, and making sure that we can understand how the forces would, is it arching action, not arching action? What are some of the different fixities that you have? How does that correlate to the overall forces that you need to design for? Then that really does require us to also understand where the different movement joints are, understand that the lintel elements are going to be more like a fixed end condition, and then with that, how the forces kind of move through. So just looking at a really quick case study for the construction, you can see that for buildings like this with many different repetitive openings, again having some of that continuity, requiring some of the reinforcement for these lintels to be continuous so that it can be a continuous beam element that can be supported at these limited column locations, can give us a very nice overall design. So here, looking at some of the different ways that we can get more capacity out of masonry lintels, using the right strength of masonry, F''M, consider maybe even going to a higher strength masonry for lintels, depending on the different situations and designs that we have to consider. Making sure that our movement joints or control joints are away from the opening, so that we can consider arching action or arching behavior. Especially if you have a finite element analysis, you can see what some of that arching behavior and see what some of the different implications to the forces and designs that you would have. You could also consider deep beam options for masonry if we have sufficient height above the opening. Certainly considering deep beam options would be a nice option for design. To increase moment capacity, certainly considering those ends being fixed certainly increases the capacity of the masonry lintel for the depth that you're considering. Certainly you could just add more depth, which would be step number 6 under increasing shear capacity, making sure that you have sufficient capacity by simply adding more courses with grout. That adds more depth. If you do have limited depth lintels, certainly you could add stirrups to that design, but what we try to encourage designers to do is look for designs without stirrups. Stirrups are additional elements that we have to add and complicate some of the construction. So if we can do our designs without stirrups, that can be very nice. Some of the different detailing requirements for masonry lintels. Here you can see, where the reinforcement would be laid out. If we have top reinforcement, how that would be implemented in with a bond beam block at the top. Again, any middle courses here, you can see just one middle course Could be any of the different types of blocks. And then the lintel block just being used for the bottom course. You can see where the reinforcement is going to be laid out. Also considering what some of the different covers would be, different types of blocks really would have to be considered. The different geometries of those blocks, where can the reinforcement actually be placed in these different type of blocks, what are some of the different clear distances that's required by code, but then what are some of the clear distances that are going to result just because of the different types of lintel blocks that are being produced today. So again, remembering our different types of options. Again, if we have fixed end beams or finite element analysis, we know that we'd have negative end moments. Top bars would be very common in those designs for all masonry lintels, whether they're simple or fixed end analyses. You're certainly going to have bottom bars, bottom positive reinforcement, positive moment reinforcement that you'd have to consider. Lastly, we can consider stirrups if we have a limited depth element, making sure that we consider the ability to add stirrups to increase the overall shear capacity. You could have a single leg or double leg, but only when more depth isn't an option. So masonry versus other lintels. Again, masonry lintels have many advantages. They're integrated. They have heavy load resistance. They're complex, but if you have the right tools, you can certainly understand the analyses, which can be a little bit complex. It's going to lead to a much more efficient design, much lower carbon footprint, a lot easier to build. Contractors that are building with masonry lintels certainly are very pleased with the increased performance construction-wise, but then also increased performance in terms of how robust they are. The challenges or the perceived challenges have really been resolved with prefabbing or some new and current shoring methods. So any of those challenges are really being diminished, if not completely eliminated. In other materials, again, they have a perceived, more capacity, but really they have to be designed for far higher loads. So really they don't have more capacity. You don't have to have other shoring in place, but I think what you give up is far more than just resolving the shoring issue, because like I said, we can prefab and we can utilize external shoring options for our designs. Because those other lintels have a lot more challenges. There's a lot of cracking, bearing issues, thermal issues, performance issues, construction issues, just overall cost. Here we looked at some cost numbers for different elements, steel lintel elements, and masonry lintel costs. You can see that all the different options from 8-inch to 48 inches for masonry lintels are less money than several of the different common steel lintel options. So again, this is going to be different for different areas, but then there's all kinds of other parts of the cost. When you have steel lintels, you have face shells, you have anchors at the top, you have unique U-bars and conditions at each support. So what are some of all the other costs that would need to be considered? We have costs here where we just looked at a pretty standard 8-foot wide by 7'4" high door, what the steel lintel cost would be for that design and what the masonry lintel cost would be. Again, these costs would going to fluctuate in different areas. I'm just trying to show you the 40% less cost for masonry in this design than the steel alternative. If the opening gets larger, some people perceive that would make it worse, but it actually makes masonry even more effective. Again, making sure that we can consider arching action, making sure that the analyses can be favorable for the masonry lintel option, so the entire wall can be supporting the loads and not just a limited area above an opening. So again, with the different types of materials and options that are out there, we know the relative costs that is going to be best for the masonry lintel. You have different cost multipliers if you would consider other types of elements. And if we look at just from a conclusion, certainly you have different types of materials that are available for lintels. We have the masonry lintel option, which is certainly going to be the best option for our designs. Precast is another good option. Again, just making sure the coordination and scheduling is considered in the overall aesthetic, making sure that the precast aesthetic would be also available. Masonry lintels are going to be integrated. They're going to be robust. They're going to be a much higher capacity, much lower carbon footprint. So obviously that's going to be a strong reason for considering. We have a lot of different software tools. Masonry and TEDs are going to be nice tools. but then also considering RAM elements, RESA floor, 3D, Tekla structural design are all going to be really nice options for doing our masonry lintel design. So with that, we're going to wrap up. If you do have any questions, please contact me at sam@forceconsulting.com. Thank you.